Hello everybody, welcome to the second lecture on compound stresses under module 2 of strength of materials. The code is 15CV32, which is common for both civil engineering as well as mechanical engineering. In the last class we had a discussion on the introduction of compound stresses, the state of stress at a point and general two-dimensional stress system. In the last class we had a discussion on the introduction, the general stress at a point, then general two-dimensional stress system. We had discussion on this. Then how do we get the two-dimensional stress system, which is a plane stress. Then we had this discussion on how to transfer the stresses on any plane which is inclined at an angle of theta with respect to vertical, and we derived these expressions for normal stress along the x dash axis, then the normal stress along the y dash axis, and the shearing stress along x dash and y dash, that is tau x dash and y dash, which is given by this expression, okay. Now, and then we solved a few problems on how to get the normal stress and the shearing stress on any given plane which is inclined at an angle. Okay, we solved this by using from the first principles, and then we solved by using the equation that we had derived earlier. So if you recall that, okay, we had solved two problems, 7.1 and 7.2. Today we would continue from where we had left. I'll start with these two problems. We will look into it later if we have time. So we will start with what is principal stresses and principal planes. Now what are principal stresses? In the last class when I derived, we had determined the normal stress on a plane which is inclined at an angle of theta, and then the shearing stress along that plane which is inclined at an angle of theta with respect to vertical. Now if the normal stress acting on any plane, if it is maximum, that stress is called as the principal stresses, and the plane on which it will be acting would be the principal plane. Now when do we call the stress to be principal stress? The stress acting on any plane is called as a principal stress when the shearing stress acting on that plane is equal to 0. So let's see what we are going to get when we take up this. So if you remember, we had derived this expression for the shearing stress as tau equals minus sigma x minus sigma y by 2 into sine 2 theta plus tau xy cos 2 theta. This is the expression that we had derived in the last class on a plane stress element subjected to the stresses as indicated in this diagram, that is sigma x positive along the x axis, and sigma y is also positive. The positive means it is tensile stresses. Then the shear stress tau xy acting like this. This is the positive sense of the normal stress and the shearing stress, and we had derived the expression for the plane which is inclined at an angle of theta with respect to the vertical as indicated here. Now as I explained, the plane on which the maximum stress occurs is called as the principal stress. Now how do we get that? As I told you, if the shearing stress acting on any plane, if it is equal to 0, the normal stress that is going to act on that plane is called as the principal stress. So the shearing stress, we have got this expression for the stress acting on this plane, that is, if this is the normal stress sigma x dash and this is tau x dash y dash, we got the expression for tau x dash y dash for any plane that is acting on this as this equation. So if I want to get what is the principal plane, then your shearing stress has to be equal to 0. So we will equate this shearing stress to 0. So 0 is equal to minus, we would take the same expression, so minus sigma x minus sigma y by 2 into sine 2 theta plus tau xy cos 2 theta. So if I solve this equation, I would get sin 2 theta by cos 2 theta equals tau xy 2 tau xy divided by sigma x minus sigma y. Now, this is nothing but tan 2 theta which is equal to 2 tau xy by sigma x minus sigma y, where this angle theta would give me the inclination of the principal plane, that is the plane on which the normal stress would be the maximum stress. So, corresponding to this angle theta, the stress that is going to be acting normal to that plane would call it as the principal stress. Okay. Now, with this, if I take this, we can write this triangle where if I represent this as 2 theta, then according to this tan 2 theta is tan is opposite by adjacent. So, this would be 2 tau xy and this would be sigma x minus sigma y. So, according to the right angle triangle Pythagoras theorem, I can find out what is the hypotenuse using this, which I would get it as sigma x minus sigma y whole square plus 2 tau xy whole square under root. Now, from this I can also find out what is cos 2 theta, which would be equal to sigma x minus sigma y divided by sigma x minus sigma y whole square plus 4 tau xy square under root, as well as sin 2 theta which is equal to 2 tau xy divided by sigma x minus sigma y whole square plus 4 tau xy whole square under root. Now, why I have done this? Now, what we have got here is the principal plane. Now, if I want to find out what would be the equation for the normal stress, okay, which would be maximum, then we have the expression that we have derived in the last class. This is the shearing stress. So, equating this to 0, we have got the expression for the principal plane, which would differ by 90 degrees. There will be two principal planes, one if it is theta, the other one would be 90 plus theta or 90 minus theta. Okay. Now, what would be the stress, normal stress that is going to be acting on this plane? If I want to derive that, then we need this expression. So, I have got this now. So, to get the equation for the normal stress, which would be the maximum value, which is called as a principal stress, let us take the expression for the normal stress acting on the inclined plane, which we had derived it in the last class for a stress system, for a plane stress system, which is indicated in this diagram. So, for that we had represented that as sigma n equals sigma x plus sigma y by 2 plus sigma x minus sigma y by 2. This expression we had derived it in the last class into this cos 2 theta plus tau xy sin 2 theta. This is the expression that we had got for the normal stress on any plane. Now, we have got this expression where this theta values corresponds to the principal planes. So, we will substitute this for cos theta as well as for sin theta. So, if we substitute this here, I would get the stress on the plane, which would be the maximum stress, which is called as the principal stress, and we denote that as sigma 1. So, this would be equal to sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 into, I am substituting for cos 2 theta as this, which would be sigma x minus sigma y divided by the value whatever is given here under root, I will not write that because it is there over here, plus tau xy into, for sin 2 theta I am substituting this equation, which would be 2 tau xy divided by the root whatever the equation that we will get here. So simplifying this, we will get this as, so we have this as we get this as sigma x plus sigma y by 2 plus, now in this 2 we have this as common. So if I take that out and multiply this with this, we would get this as sigma x minus sigma y whole square, which is common in this, divided by 2, and here plus we have this which is 2 tau xy whole square. This entire thing is going to be divided by this whatever we have it under root. This is what we get. Now simplifying further, we would get this as sigma x plus sigma y by 2 plus, if you observe this, if I take this 2 to this, I would get this as 4 tau xy, and divided by this half would come out. So this would become half sigma x minus sigma y whole square plus 4 tau xy whole square divided by, we have this which is under root. This is what we are going to get. So further simplification, I would erase this and we will see what we are going to get. So further simplification of this, we would get sigma 1 to be equal to sigma x plus sigma y by 2 plus sigma x minus sigma y whole square plus 4 tau xy whole square under root, and we have half also here which comes out of the thing. So this is the expression for the principal stress, which is the maximum principal stress. Now to get the minimum principal stress, this would differ by this would become minus. So we get sigma 2 to be equal to sigma x plus sigma y by 2 minus half of sigma x minus sigma y whole square plus 4 tau xy under root. So this would be the normal stress acting on the principal plane, which is given by this equation. This would be the maximum principal stress, this would be the minimum principal stress equation. Now if you look at this, the principal stress occurs on principal plane of stress with 0 shearing stress. So when I substitute that, we get the principal planes. Using this principal plane, we would get what is the equation for the maximum and the minimum principal stress, which will differ by plus or minus as indicated in this. Okay, and this equation would give the principal plane inclination, the theta p value. Okay, now the theta p defines two angles separated by 90 degrees. So you can see in this diagram. So for the stress that we have indicated, theta p would be this, the stress, the normal stress that is going to be acting would be the maximum stress, which is denoted as sigma 1 or sigma max, and normal to this plane you will have the normal stress, which would be the minimum stress that is going to be acting, which is the minimum principal stress. Now this angle would be equal to theta p plus 90 degrees. That is what we get from this. Okay, so this equation gives us the maximum and the minimum principal stress, whereas this equation would give us the inclination of the principal planes. Okay, so now coming to maximum shearing stress. Okay, we will look at maximum shearing stress, how it is going to occur. So I will use the blackboard again. So we have got from the normal stress what is the maximum principal stress and the minimum principal stress. Then from the shearing stress, equating the shearing stress equation to 0, we have got what is the principal plane. Now let us see how to get the maximum shearing stress. So to get the maximum shearing stress, we would once again use the equation which we have got earlier for the general two-dimensional plane stress element. Okay. So again we will take the same expression tau, what we have derived earlier, where we have this minus sigma y by 2. This equation we have derived it in the last class, sin 2 theta plus tau xy cos 2 theta. Now to get the maximum plane, principal plane, we have equated this to 0 and we have got the value for the maximum principal planes. Now to get the plane where we will have the maximum shearing stress, I have to differentiate this with respect to theta and equate that to 0 to get the maximum value. So when I do that, this is what I am going to get. This is equal to minus sigma x minus sigma y by 2 into sin 2 theta is cos 2 theta into 2 with a positive sign. We have, oh sorry, this is negative. So no, this is positive. When I resolve this, plus tau xy cos 2 theta is minus sin 2 theta into 2. This is what we get. Now this equation is again equated to 0. So 0 equals, we get this as minus sigma x minus sigma y by 2. And we have 2 here, so 2 cos 2 theta. Now there is a negative sign here. When I multiply with positive, it becomes minus tau xy into 2 sin 2 theta. So if I rearrange this, I would get the expression for as tan 2 theta, which is equal to minus sigma x minus sigma y by 2 tau xy. This is the expression that we get. Now this would give us what is the maximum the inclination of the plane on which we will get the maximum shearing stress. Okay. Now this equation is used to get the inclination of the plane on which we will have the maximum shearing stress. Okay. Now what would be the corresponding normal stress on this plane? We are going to derive that in the next equation. Okay. For that, again, as I did it in the last class, we will take the triangle where you will have it like this. This would be 2 theta s, where this s corresponds to the maximum shearing stress plane, and we have tan equals sigma x minus sigma y, and this is 2 tau xy. Okay. From this, if I take cos 2 theta, I would get this as 2 tau xy divided by this would be sigma x minus sigma y, as we did it in the last this thing, plus 2 tau xy whole square under root. So this is what we get the same thing here. Similarly, sin 2 theta would be equal to sigma x minus sigma y divided by whatever we have under root. That is what we get for sin 2 theta. Now using these values for cos 2 theta and sin 2 theta, we would derive the expression for the normal stress acting on the maximum shearing stress plane. Okay. So for that, again I will erase this and we would take the equation for the normal stress on any plane, which is equal to sigma n. Earlier we have this okay. So the values to get the shearing stress value, we have this equation tau equals minus sigma x minus sigma y divided by 2 into we have sigma x minus sigma y divided by whatever root is there, that is because of this sin 2 theta plus tau xy into cos 2 theta. Cos 2 theta is given by this expression, which is 2 tau xy divided by root whatever is there here. So, if I analyze this, I would get, or if I solve this, I would get this equation as tau equals plus or minus half of sigma x minus sigma y whole square plus 4 tau xy whole square under root. Now, this expression would give me the maximum shear stress and minimum shear stress on the maximum shear stress plane and the minimum shear stress plane. Now, if you look at this expression and this expression here, this is tau max, which is denoted as R equals sigma x minus sigma y by 2 whole square. That is what we have here, sigma x minus sigma y square plus 4 tau xy whole square. I have written it here. So, if I take 4 out, then I will get this to be tau xy divided by 2. If I take this 2 inside, I get here to be 2 and this 4 will get cancelled. And we have derived this expression, which is the shearing stress value, the plane theta s is the plane. Now, this also defines two angles separated by 90 degrees and offset from theta p by 45 degrees, and the average shear stress that is going to be acting is given by this expression, which is sigma x plus sigma y by 2. Now, this would give you the planes on which the maximum shear stress is going to act. So, you can see here this is tau max, which is the shear stress acting on this plane and this plane. The angle at which these are there is theta s, which is measured from the x axis. Since it is negative, it is measured in the positive anti-clockwise direction or clockwise direction, clockwise direction. Then this plane would be at an angle of 45 degrees. The difference by theta p would be 45 degrees, whereas from this where the normal stress is there, this and this would be at 90 degrees to each other. So, we have derived expression for the maximum normal stress, which is called as the principal stress, and as well as the minimum normal stress, which is also called as the minimum principal stress. The angle for the maximum principal stress and the minimum principal stress, then the maximum shearing stress and the angle at which this is going to be inclined. So, we have derived these expressions, and now let us see how to solve problems using this. So, this is one problem. For the state of plane stress shown, determine the principal planes, the principal stresses, the maximum shearing stress and the corresponding normal stress. So, this is the problem. So, the solution for this is obtained like this. So, we know that the equation for the inclination of the principal planes is given by this equation. So, we are going to use this equation. Then we also know what is the formula that should be used to get the value of the principal stress, the minimum and the maximum values, which is given by this equation, which I have derived it just now. Then we also derived this expression, which gives us the maximum shearing stress value and the average shearing stress value, which is given by this. This would be the value or the stress, normal stress, that is going to be acting on this plane, where the maximum shearing stress is going to be acting. So, these are the equations that we are going to use to solve this. To solve this problem, we are going to use these equations. Okay. So, let us see what is that. Okay. So, we have, see, in the earlier this thing, 40 megapascal is the shearing stress acting, which is positive. 50 megapascal is the normal stress, which is sigma x, which is positive, whereas 10 megapascal is compressive, which is negative. That is what is indicated here again. This is the values that is given. So, solution is, we have this equation for the principal planes. So, substituting here 40 for tau xy, it is positive, then sigma x is tensile, so it is positive. So, substituting it as 50 minus sigma y, this is the equation that we have, minus sigma y, but sigma y is compressive here. So, we have to substitute it as minus 10. So, if I substitute all this, this value that I am going to get is 1.333. So, if I want to find out the value of theta, so 2 theta p equals tan inverse of this value, which we will get it as 53.1 degrees and 233.1 degrees. So, theta p would be equal to 26.6 degrees and 116.6 degrees, which is differing by 90 degrees, whereas here this differs by 180 degrees. So, the same values are given here. So, this would be theta p, which is equal to 26.6, which we have got, whereas this plane, if I find out this angle, this would be inclined at an angle of 116.6 degrees. Now, let us see what would be the corresponding normal stress values, which is indicated here as sigma max equals 70 megapascal. How do we get this? This we got it because of this. To determine the principal stress from, we know this equation which we have derived just today. So, this would give you sigma max and sigma minimum. So, substituting the values here, we have sigma x as 50 megapascal and sigma y as minus 10 megapascal divided by 2 plus sigma x is 50 megapascal minus of minus 10 divided by 2 and tau xy as 40 megapascal. If I substitute these values, I would get the value as this, where sigma max is equal to 70 megapascal, which is indicated here, which is positive. Then sigma minimum, we will get it as minus 30 megapascal, which is indicated here. So, this gives us the plane on which the normal stress would be maximum, which is inclined at an angle of 26.6 with the x axis, one plane, the other plane would be inclined at an angle of 116.6 degrees. The normal stress that is going to be acting on this plane is 70 megapascal, which is positive, whereas on this plane it would be compressive and the value is 30 megapascal. So, this gives us the principal planes and this gives us the normal stress acting on the principal planes, which are the maximum and the minimum stresses. Now, this equation is used to find out the maximum shearing stress. Now, we derived this expression also just now, which is on the board. So, substituting the values, sigma x is 50, sigma y is minus 10. So, 50 minus of minus 10, okay, divided by 2, which we will get it as 50 plus 10, 60 by 2, which is 30 whole square, and tau xy is positive 40, so 40 square under root. So, we get the value as 50. This is the maximum shearing stress value. The corresponding inclination or the plane on which this maximum shearing stress would act is, as we discussed, it is theta s, which would differ with respect to the principal plane by 45 degrees. So, principal planes we got it as 26.6. So, minus 45 we get it as minus 18.4 and the other plane was 116, minus 45 we get it as 71.6. So, the stress block would look something like this. So, this is the shearing stress sigma s, which is equal to 18.4. The corresponding shearing stress value is this tau max, which is 50 megapascal. Now, the next, to find out what would be the normal stress acting on these planes, okay. So, that would be the average shearing, average stress values, which is given by this equation sigma x plus sigma y by 2. Sigma as we have it as 50, sigma y is minus 10. So, it is 50 minus 10 divided by 2. We get this as the normal stress that is going to be acting on the maximum shearing stress plane. So, this is what we get. Okay. So, we have solved all the required ones, that is principal planes we got it as this. Principal planes, we got it as 26.6 and 116.6, that is from the principal planes. Principal stresses, we got it as this, which is 70 and minus 30 on these planes, which we have derived. Then the maximum shearing stress and the corresponding normal stress, we have got it from here. The maximum shearing stress is 50 and the corresponding planes are given by this values, minus 18.4 and 71.6. Now let us go to the next problem. Now here we have taken, I have taken the stresses like this. The stress acting along x is equal to 0. The stress acting along y is positive, that is tensile stress, which is 56.6 megapascal, and the shearing stress that is acting is also positive, which is equal to 50.9 megapascal. So what we are supposed to do is, we are supposed to find out the principal planes and the principal stresses. So principal plane equation is given by this. So here tau xy is equal to 50.9 and it is positive, we have substituted the same here, whereas sigma x is 0, so 0 is substituted. Sigma y is positive because it is tensile, so we have substituted the same thing, minus 56.6. So we get this as minus 1.8. So from this we would get theta p, which is the principal plane, which is equal to minus 30.5 and 59.5, which differs by 90 degrees. So the same thing is indicated from this diagram. The principal plane is inclined at minus 30.5 and 59.6. This is minus 30.5 and this is if I find this would be angle which would be equal to 59.5 degrees. So to find out the normal stress acting on this plane, we have this equation, which is sigma max comma sigma minimum equals this equation. So substituting this with these values, sigma x equals 0, sigma y is 56.6, that is what we have substituted and it is positive, and tau xy is 50.9 and that is also positive. Substituting that, we get the sigma max value and the sigma minimum value. Sigma max is 86.5 megapascal and sigma minimum is minus 29.9 megapascal. So for this problem, we are supposed to find out the principal plane and the principal stress, which we have got it from this equation. Okay, we have solved two problems now. Let us go to the next one. Okay, in this problem again, what is given is, for the given state of stress, determine the principal plane and the principal stress. So here we have sigma x to be minus 60 because that is compressive. Sigma y is also compressive, the value is 40 megapascal, whereas tau xy is positive, okay, which is given by 35 megapascal. So using the equation for the principal planes, we would get this as minus 37.6 degrees and 53 degrees. So if I have to find out the maximum principal stresses and principal plane, we use this equation. Okay, sigma x is negative because it is compressive, minus 60 is what is substituted. Sigma y is also negative, which is minus 40, which is substituted here, divided by 2, plus or minus because we are finding out the maximum principal stress as well as the minimum principal stress, and then sigma x minus 60 minus of minus 60, which becomes positive. This is plus because it is minus sigma x minus of minus 40, so it is plus 40 divided by 2, whereas tau xy is positive, so 35 whole square. So from this equation, if we simplify, we get sigma max equals minus 13.6 and sigma minimum is equal to minus 86.4. Both of these are negative. So what are we supposed to find is the principal planes. The principal planes is minus 37 and plus 53 degrees, and the principal stress is minus 13.6 and minus 86.4. Both of them are compressive. Let us go to the next problem. Again here we have to find out the principal planes and principal stress. The sigma x value is this, which is positive, that is tensile, 28 megapascal. Sigma y is also positive because that is also tensile and it is 140 megapascal, whereas the shearing stress is negative because it is opposite to what we have taken it while we have derived the equations. So, that is minus 42 megapascals. So, to find out the principal planes, we have this equation. Substituting these values in this equation, we would get the inclination of the principal planes, which is positive 18.43 degrees, and the other plane is 108. These two differs by 90 degrees. Now, to get the principal stress values, sigma max and sigma minimum, we have this equation. So, substituting these values in this equation, we would get this as 28 plus 140 divided by 2, because sigma x is positive 28, sigma y is also positive 140. So, divided by 2 plus sigma x is 28 minus 140 divided by 2 whole square plus tau xy value is negative. So, minus 42 is substituted here. So, from this we get the maximum principal stress and the minimum principal stress. Now, you can see that these two, both of them are positive, which indicates that it is tensile stresses that is going to be acting on the principal plane, which is inclined at 18.4 degrees and 108.9 degrees. Now, we have to look at what is the derivation for Mohr circle. So, this what we will do is we would take up this in the next class because we are running short of time. So, what I will do is I will just recap whatever we have done today. So, what we have looked at is we have looked at how to derive the expression for principal stresses and principal strain from the previous class, where we had the normal stress equation. From that we have derived the principal stress formula, which is given by this equation for the maximum and the minimum, which differs by plus or minus with this value. The plane on which it is going to be acting, that is tan 2 theta p, which is given by this. Okay. Then the inclination of the principal plane and the normal stresses acting on this plane is indicated as this. Now, to get the maximum shearing stress values, we have again derived this, where we have taken the shear stress which we have derived in the last class and differentiating that with respect to theta p, we had got the expression which is indicated here on the board, and that expression is given by this, which is tau max equals sigma x minus sigma y by 2 whole square plus tau xy whole square under root, and the corresponding plane on which the maximum shearing stress is going to occur is given by this equation, tan 2 theta s equals minus sigma x minus sigma y divided by 2 tau xy. The two planes are going to be separated by 90 degrees with respect to each other, whereas with respect to the principal planes it is going to be offsetted by 45 degrees. The normal stress that is going to be acting on the maximum principal stress plane is given by this equation, that is sigma x plus sigma y by 2, and that is what is indicated in this figure. And we have also looked upon the values how to get from for the given stress forces. We have solved 4 problems. One is this, where we got the values for the principal stresses and the principal strain, and how to indicate this principal stresses and principal strains, principal stresses and the plane, principal plane is given by this equation, this diagram. Then we had also looked upon what is the maximum shearing stress, which is given by this, and the stress block for the maximum shearing stress and the corresponding normal stress acting on that plane, which is given by this. And in the second problem we have solved and we have found what is the principal plane and the principal stress values. Okay. And we have derived or solved these 2 problems also today. So, we have to go for next derivation or to find out the maximum and the minimum normal stresses using Mohr circle. I think we would not be able to solve this today, we would look at this in the next class. Okay. If you have any doubts, you can always send an SMS or send a email to VTU website, and I would be glad to answer those questions. Okay. Thank you very much.